Okay, we considered normalized LMS algorithm, NLMS. We discussed its convergence, derivation, convergence, approximately convergence. That is, it acts like LMS algorithm actually with mu, time varying mu, with a mu which is different now, mu by tracer, and so that effective mu will have upper bound for convergence as 2. Mu should be greater than 2, less than 2, greater than 0. All these were discussed. I also showed that if the input is highly correlated, then that NLMS algorithm requires many iterations to converge. But if the input is white, then they converge ideally in the absence of noise just in 2 steps. But for general input which has lot of correlation, highly correlated input, NLMS algorithm suffers from poorer convergence. Okay. So, a better alternative here is a generalization of the NLMS algorithm called affine projection. APA. Again here we will assume all the real case, no complex data, and though all this can be extended to complex case also, but we will not consider here in this course. And also to start with, we will not assume any noise. So, you remember what we had in the case of NLMS, if we had just 2 coefficients W0 cap and W1 cap, and there is no noise. So, what was coming out was Dn and this is Xn. Okay. So, since we do not know these coefficients, we take general W0 and unknown W0 Xn plus W1 Xn minus 1 equal to Dn. Okay. So, there are infinite solutions. This actually gives a straight line, we have seen. Okay. And any point on the straight line is a solution, of which this is also a valid solution. Okay. But only thing we do not know. Then of course, you remember the procedure that if Wn is the current estimate, then from Wn we try to arrive at a point on this straight line. Okay. So, that this equation is satisfied, but distance from that point to Wn is minimum, that is it is orthogonal, perpendicular to this line, and so on and so forth. In fact, you can see one thing, if we have 3 coefficients, suppose consider this case where I have got 3 coefficients. The same logic will hold. Here it will be W0, general W0 Xn equal to Dn. So, this is it has 3 axes W0, W1, W2. So, 3 dimensional plot, and this will be a plane. So, it could be a plane like this. This is a plane, and somewhere in the plane I have got this point, optimal point. This point, and then we take a Wn, then we project on this plane. Earlier it was straight line, now we project on this plane. This we take to be Wn plus 1. Then we move to n from nth index to n plus 1th index, you get another plane. So, you project this point, this vector on that plane, get Wn plus 2, and so on and so forth. Okay, but at a time, at any index, you just are considering only one plane, and on that you are projecting the previous weight vector or current weight vector rather. Okay, we are projecting orthogonally, and that is how you do. In the case of affine projection, we generalize like this. Here, just consider a general case. These are true parameters, general case. You have got Xn, and in the absence of noise, you have got Dn. Since I do not know these coefficients, the general equation I write, it will be in terms of these unknowns W0 x n plus equal to dn, okay, which also you can write as W transpose x n equivalent to x transpose n W is equal to dn. W of course is that coefficient vector, unknown coefficients, we have to determine the true values, and x n is the data vector at the current index n, that is current data and some of the past data. So, this is a simple FIR filter output equation, this is what you have. Now, in the case of APA, we try to find out this W0 to Wn minus 1 not just from one plane, in fact, I should call it hyperplane because it is more than 3 dimension. Plane is in the 3 dimensions. So, let us just use the term hyperplane. So, we try to find out W0, W1 and this Wn minus 1, all these not just from one hyperplane. We assume that okay, since the coefficients are not changing at the previous clock n minus 1th clock also, if I have this, that is at n minus 1th clock, if I input x n minus 1, then the corresponding filter output will be filter coefficients are not changing. For the same coefficients at nth clock, these are the data, and you get W transpose x n dn. At n minus 1th clock, it should be dn minus 1, that is W should be such that W transpose x n at nth clock should give you dn, the dn that is coming out. W transpose at n minus 1th clock, it would give you dn minus 1. So, simultaneously this should be satisfied, this should be satisfied, this one, this one, this one. That is at nth clock W should satisfy this equation, same W should satisfy at n minus 1th clock this equation, and dot 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 like that up to we go p terms n, n minus 1, n minus 2 up to maybe n minus p. Okay. P is called projection order. So, I am looking to solve for or obtain a W which will simultaneously satisfy not just one hyperplane or one equation, one plane or one straight line in the case of 2 dimension, it will satisfy multiple such planar equations, hyperplane equations. Okay. At nth clock, n minus 1th clock, n minus 2th clock, dot dot dot, n minus pth clock simultaneously. That means, wherever they intersect, my W must belong there, because the planes. To explain that, let me consider just 3 coefficients. Only let me consider 3 coefficients. Suppose we have one equation which is W0 x n plus W1 x n minus 1 plus W2 x n minus 2 equal to dn, that is in short W transpose x n is dn, and at n minus 1th clock you have got W transpose x n minus 1 vector, that is x n minus 1, n minus 2, n minus 3 as d n minus 1, just 2. So, this is one plane Okay, so this is one plane. Okay, this is one plane. That is this plane, and another one will be another plane. another one will be another plane, maybe like this. So, these two planes actually will intersect. Let me try to draw a better diagram. Suppose it like this. So, this plane has, this is this plane. This is this plane and that is this plane, okay. And they intersect, the two planes will intersect at one line. That you can understand. You take two, piece of papers, if they intersect, that will be a straight line. I mean from 3 dimension it becomes 2 dimension, that is plane had 3 variables, okay. The intersection will be a straight line, we have actually 2 variables, that is obvious. You eliminate one of the 3, W0 or W1 or W2, and you get one equation, okay, from them. So, that is this equation, that is obvious. Now, here what will you do is this, that suppose your Wn is somewhere here, and optimal one will be satisfying both this equation. So, that should lie, optimal vector should lie in both the planes, therefore, it should lie on the intersection which is common to both the planes. So, maybe this is where your optimal one, this W opt, the true system parameters. Now, what you are doing, if you are doing n LMS, from here we will just take a projection on this plane. So, this will be your new vector, this will be a new vector. So, this will be W n plus 1, but you see W n plus 1 and W opt, okay. There is so much of gap, but in APA, affine projection algorithm, we will not project W n on this plane or on this plane, we will project on that intersection. In this case, because they are 3 dimensional, intersection is 2 dimensional, which is straight line. In general, if each hyperplane is, say, suppose capital N dimensional, then that intersection will be between 2 will be n minus 1, between 3 will be n minus 2 dimensional, and like that. Okay, this you can visualize easily. So, we will take a perpendicular there. So, we will be drawing perpendicular on this line, which is intersection. So, that will be my W n plus 1. This vector is W n plus 1 under APA. And now, see, this is now much closer to this optimal one than this guy. Under NLMS, I would have projected here. So much of distance between the optimal one and the projected point. But if I project W n not on this plane or this plane separately, but on the intersection between the two planes, then I hit a point which is much closer to the optimal one. So, I am already very close to optimal one. So, I will require much less iterations to reach the optimal one than the NLMS. This is the philosophy. This you can extend to the general n dimensional case. Okay. That means, optimal here the optimization will be this, we should minimize, or before that maybe some definitions will help us at this stage. These equations can be combined into a matrix vector form like this. If I define x n, where this is x n vector we already defined, okay, the input data vector at n clock, then x n minus 1 dot 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 x n minus capital N plus 1, this is x n. Then And if I define dn vector as current dn, then previous dn dot 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 last dn. Sorry, I made a mistake here. This should not be this. Every xn vector is of length capital N, but how many I have? I have x of n here, x of n minus 1 here, x of n minus 2, they are the columns. So, last is x n minus p. So, it should be x n minus p. All right, this is my x n vector. So, this is n cross p plus 1, n minus 0, n minus 1 up to n minus p. So, total p plus 1, this is matrix. Okay. Then you can see all these equations, they imply this, that x n transpose w should be d n vector, because x n transpose w, if you do the transpose of this, first column will become first row. So, column will become row means it will be a row x transpose n, x n was column, so x transpose n is row. Then will be this second column will become second row, second x transpose n minus 1, x n minus 1 is column, so x transpose n minus 1 is row, dot 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 dot, and this w, that is obviously equal to d n vector, because x transpose n w, you have seen x transpose n w, that is d n scalar, x transpose, this is equal to actually equivalent to, like above I wrote equivalent. So, here x transpose n minus 1 w, these two are equivalent. So, x transpose n minus 1 w will be d n minus 1, next guy, and so on and so forth. So, it will become d n. So, this is my equation, this is the equation, constraint. So, therefore, given w n, I will try to find out one w which satisfies this, that is, which lies in the intersection hyperplane or intersection of all these hyperplanes. That itself can be straight line or a plane, 3-dimensional plane, or a 4-dimensional hyperplane or 5-dimensional hyperplane, whatever. That depends on capital N and capital P and all that. Okay. So, I will be projecting w n to a w in that intersection hyperplane. Okay. That means, my equation will be this, I will be minimizing subject to this equation, x transpose n w equal to d n. Okay. So, this will mean this is a constraint minimization. So, again I will bring Lagrange multiplier, but remember now I have not one constraint, like in the case of NLMS just one straight line. So, I had one constraint, I have one here, next here, total p plus 1 constraint, that is this should be satisfied, simultaneously this should be satisfied, simultaneously next will be satisfied, okay, simultaneously. So, I have one constraint here that will require one Lagrange multiplier, say lambda 1. Next is this, that will require another one, okay, and like that. That means, I will now consider a general function w, and you can call it lambda vector. Lambda vector has got all the Lagrange multipliers required. 1 minute. In minus 1, okay, fine. So, lambda 0, lambda 1 dot 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 lambda p. That is, we should minimize this subject to first use lambda 0, that is constraint is x n transpose w minus d n, then lambda 1. These are all Lagrange multipliers. Earlier I took only one, now I have got so many because of these constraints. Because you see, if I differentiate this with respect to lambda 0 equate to 0, all other fellows will disappear, only this will remain and that will equate to 0. So, that condition will be satisfied. If I differentiate this with respect to lambda 1, then this quantity, this will result and that will be equated to 0, others already disappear. Okay. So, this second constraint, next constraint will be satisfied, so on and so forth, plus dot 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 dot, last one is lambda p x transpose all right. So, this I have to minimize. So, this I can, you can see I can write in this form, first term remains as it is, then if I say lambda transpose times x n, we will verify, minus d n. W vector minus d n vector. Let us see. This we have seen in the previous page. This is the constraint. Okay, that is x transpose n w should be equal to d n. You can even go into term wise, x transpose n w minus d n. So, this part will be what? This part will be a vector like this, x transpose, we have already seen in the previous page, minus d n, then x transpose n minus 1 minus d n minus 1 dot 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 dot. I already discussed a while ago. So, this is this vector, matrix into column vector is a column vector minus again column vector. So, total is a column vector. This is a row vector, row into column is a scalar. All right. So, this is x n transpose, x n was a column vector, x transpose n w, this is a filter output, that minus d n. Okay. I do not know w. So, I should have a w which satisfies this, this is equal to 0. Now, if I have lambda transpose now, if I have lambda transpose, just transpose it. So, it will be a row vector lambda 0, lambda 1, lambda p, lambda 0, lambda 1 dot dot lambda p. So, lambda 0 will multiply this. So, that is what I will get, this term plus lambda 1 times next. So, we will get this term and dot 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 dot. So, this is actually entire equation we can write like this, okay, compactly, but actually this is this. The moment I differentiate L with respect to lambda 0 equate to 0, this only this much will remain. So, this will become 0. So, x transpose n w will be d n. So, that constraint will be satisfied. If I differentiate this with respect to lambda 1 equate to 0, only this part will remain and equate to 0 means it will lead to x transpose n minus 1 w equal to d n minus 1. So, then the second constraint will be satisfied, so on and so forth. But this whole expression I am writing in a compact manner like this. All right. So, with that I can go to the next page and first let me rewrite this. Equal to Okay. So, I know del L del lambda k will simply satisfy this x transpose n minus k w n minus k, and this we equate to 0. So, this constant satisfied. All right. Yeah. So, separately we have to carry out this other partial derivatives also, that is del w L, and that is partial derivative of this with respect to each component of w, put it in a stack, and that again you have to define, equate to 0, there is a 0 vector now. So, this actually will lead to the value of lambda. So, all this we will do in the next class. Thank you very much.